So for those of you who haven't seen this article, Nature did a profile on Stefan. Actually, it's a long piece, and given his work in the desert, it's been really remarkable what he's been able to achieve. But more than anything, it's a very interesting piece to read, in no small part because in that article is laid out very clearly sort of what is the objective of this meeting, which is to sort of understand how African climate made this transition from being very wet to very dry. And so Stefan has contributed a big part of his career to studying this, and it's a great article to read. So for those of you who want to see it, I'm happy to send it around. Sorry, I've got to stay here. One of our interests in working with ocean sediments is that as the world's repository of the sediment load coming from the continents, the oceans provide us a continuous and a complete archive of past climate change. So even though they're far from the points of interest, for example, from Lake Yoa, where Stefan was giving his talk, I think the oceans really have a lot to offer us in terms of being able to piece together these sort of complete and continuous and also multiple records of climate change. So we're not really restricted to recovering a section from one particular geographic region, but rather we can actually really exploit the depositional environment around the entire perimeter of the North African subcontinent. So this will be my talk. It's the African Humid Period, A View from the Ocean. And really this talk is representing the collective efforts of many, many, many people. A few of whom are listed here. Jess Tierney has been really instrumental in bringing the molecular biomarker approach to this particular problem, and is proving to have a sort of a revolutionary influence in terms of our understanding of past climate change. David McGee is an assistant professor at MIT right now, who's contributed a lot of work on thorium normalization of particle fluxes, particularly dust fluxes off of West Africa. And Jan Bernd Stutz has also contributed on the grain size work. And Louisa Brattmiller, I'll be showing some of her work that's currently in review right now, as well as Jenna Cole, a former postdoc. So an overview of where I hope to go in the next 40 minutes or so is to give you a summary of what we believe to be the evolution of climate over North Africa, spanning the last 25,000 years or so. To address these 5 problems here, first of all is the spatial extent of the African humid period, particularly off of the West African margin. To address the timing and the abruptness of transitions, much of this will mirror Jess's conclusions. Some new results from Louisa Brattmiller in our group has been looking at ocean productivity changes. This is useful because off of West Africa, this is a wind-driven phenomenon. It's wind-driven coastal upwelling. And so since we're talking about dust, and dust is transported by the winds, the history of the winds proves to be actually an important part of this puzzle that I think will help us reconcile the differences between some of the records from the interior of North Africa and those on the side. One of the, I think, central messages that's going to come through with this is that there are 2 influences of African climate. One, of course, is the orbital forcing of the monsoon, the low latitude forcing of the monsoonal circulation. That constrains the timing, but much of what we see in terms of the abruptness of the onset of the humid periods can be related to actually the impacts of high latitude forcing that basically defines the edges of these transitions. And then last, I'm going to just wrap up with an observation on some of Jess's results that she didn't cover, but she would have if we'd been talking about this, but it actually ties into the dust records really well. So this is a paper that Jess and I wrote for Nature Education that is just an overview of some of the evidence for the African humid period. But of course, we have very good records of maximum interior lake level extent, not only over North Africa, but of course extending into East Africa as well. And Yannick Garcin is going to give us some just beautiful results from his work in Lake Turkana. So there's no question that the African humid period was widespread, and we know have a very good reason that it's paced by orbital precession. This is a histogram of lake levels over the last 20,000 years. And of course, when we go into the interior to look at these sites, this is a photograph from Neil Roberts. We saw a much nicer one from this morning. The problem with working with some of the terrestrial sequences is that they're commonly incomplete. And so our ability to reconstruct a continuous record of climate change going back, let's say, the last 20,000 years is hampered by these intervals of non-deposition and erosion that can give us a biased record of what we're seeing on land. And so this is to emphasize a point that has been made in many different talks. This is, if you put the US in a different configuration, you can put all of Western Europe, Eastern Europe, India, and China into much of North Africa. So it's a massive place, and just to echo the point that Stefan made, no single data point can speak to the climate of an entire subcontinent. And that counts, obviously, for Lake Yoa as well, but it's certainly true for the marine sediments, is that it doesn't reflect that too. So one of the things that we can do is that one of the classic signatures of North Africa is this strong seasonality in rainfall. And this gives us a very strong seasonality in the production of dust, which are these loosely aggregated soils that can be uplifted in convective events and carried in the tropical easterlies. They take about a week to cross the Atlantic, and they impinge upon the Caribbean over here. These dust outbreak events are carrying the dust load across the Atlantic, where much of that load is dropped over the western margin of North Africa, and then, of course, it makes its way across. The notion that dust can be a quantitative proxy for climate, or a semi-quantitative proxy for climate, is taken from these sets of observations. This is actually the historical record of dust that's collected in Barbados on dust aerosol collection towers. And this is going from the years 1966 up to 1999, but it obviously continues up to the present as well. This is the record of West African precipitation for the region between 10 north and 10 and 20 north. And you can see this transition from generally wetter conditions from the 1940s up to the late 60s. And then this is this transition that occurred in the 70s toward a drier baseline that's recovered a little bit in recent years, but it's lower than where it was in the previous decades. One of the things you can notice is that there are these periods, for instance, in the early 70s, in the mid 80s, the 90s, and then the late 90s, when there were these elevated dust flux periods. These are times when the dust loading was roughly twice of what it is on the baseline. And if you just find with these time intervals, they correspond to these this colored intervals here for the precipitation, you can see they correspond with low precip events as well. And so if you do the obvious thing and just compute the correlation between the precipitation index or precipitation anomaly index versus the dust loading and lag it by 1 year, you actually get a pretty decent correlation that links the dust flux to the absolute rainfall anomalies that occur over this pretty broad spatial area. But you can see this loading of colors here. This is where the rainfall anomalies are most closely correlated with these drought events. So the signal of this in the ocean sediments is that what we're trying to do is to quantify past variations in the export of this mineral dust as it's carried off the Sahara by in this case, the tropical easterlies, the upper level easterlies. This is actually how it would appear, and the color balance of this projector is a little different than how it appears on my screen, but it's you can see this is a sort of a broader red interval here, and then this should normally be kind of a white buff color. And this transition right around here is the end of the African humid period. So this would be about 5,000 years ago, and this would be this brick red color is the occurrence of the dust that you actually see physically in the sediment cores. So this is actually the ship that we were using. This is the Woods Hole ship, the Oceanus. It's a small research vessel, and we do gravity coring. This is about a 1-ton lead weight on here, and on the base of this is a very long tube that we use to collect the sediment cores from the seafloor, typically from a depth of about 1.5 to 3 kilometers water depth. This is this record that many of you have seen already. In this record that we put together off the coast of West Africa, we developed a geochemical way to extract the mineral dust itself, and then we called this the African humid period, extending from about 14,500 years ago, interrupted by the Younger Dryas, which is a dry period or a high dust interval, and then this broad interval from roughly 11,000 to about 5,000 years ago when it was wet, and then it became, in this particular core, became abruptly dry about 5,000 years ago. So the question was, how representative is that one data point if we were to be able to reconstruct the same dust flux records from this whole sequence here along the margin? So we actually led a cruise that we called CHEETAH. Every cruise has to have an acronym. So this was Changing Holocene Environments of the Eastern Tropical Atlantic. I know it's a stretch, but that's what we did. And so we left from Lisbon, and actually we were on our way to Senegal to collect cores off of here when one of the engines on the ship blew up, and we were on fire for a little bit, and then we limped our way into the Cape Verdes Islands here, not before taking a core. But you can see we have a really great distribution of cores to work with, and so this really gives us, for the first time, a way to do what I think you can see where we're going to go with this. We're going to try to understand how representative this one data point here, this is ODP site 658, how representative that one data point is for what would have happened along this whole margin. And as Edouard showed in his talk, he sees evidence even up by Cape Gear for past African humid periods. And so you can sort of see where we're going to go with this, is that almost this whole spread along here experienced wetter conditions during the African humid period. So this is what we wanted to know from this collection of cores, which was what do each of those cores tell us about the timing of the African humid period and how quick the transitions were. And then also try to separate this question of dry or aridity signals from changes in the wind, because dust has a problem in that it's, we have the production of dust obviously comes from rainfall deficits, but if there's no wind to transport it, that signal's not going to be seen in the ocean sediments. And so there's two things. One is the competence of the wind, and one is the existing aridity. And then, of course, the spatial signature of that aridity. And then ultimately, and this is why Jess's work is so important, is that trying to link this to actual past hydrology is so vitally important, because, in fact, that's what we're wanting to know, is how did paleohydrology change and when. So we apply a battery of measurements to try to reconstruct this, and I'll walk you through sort of each of these different data sets as they apply to these various cores. We'll look at the aeolian sediment, the thorium normalization technique for reconstructing particle fluxes, and then we look at radiogenic isotope geochemistry to get at the provenance of the dust. In other words, how big of an area are we sampling when we're looking at these dust events? Look at grain size and biogenic opal to address changes in the winds. And then I'll just leave on Jess's plant wax biomarker data to put this into context. So beginning with the first, I'd done some work with Jess Adkins about 10 years ago in trying to use this thorium normalization technique to address this question about the flux. You may remember that abrupt climate change record that I showed was just the percentage of dust that's in the record. It wasn't the actual flux. In paleoceanography, it's very easy to measure, or relatively easy to measure, the percentage of anything, but it's very hard to ascribe a physical process to explaining a percent variation, because it can just be a dilution story by something else. So for example, in deep sea sediments, half the sediments are clay and silt, and the other half are biogenic sediments. And you don't know if it's changes in aridity that are causing the observed changes or changes in ocean productivity. So we use this approach, which is thorium normalization. And the principle of it is pretty straightforward, is that the ocean is relatively loaded with uranium-234, which decays to 230 thorium. Uranium is soluble in seawater. Thorium, the daughter product, is highly insoluble and highly particle reactive. And so once this decay occurs, this thorium wants to attach or adsorb onto particles. And so if you measure the inventory of thorium down a core that's been dated, and you know the percentage of, let's say, dust in the core, you can actually calculate the particle flux of that dust over time. And that's what you want to know. You want to know what is the mass flux of dust over time. So just to give you an idea that this seems to work, in these blue squares here are the actual fluxes measured in grams of dust per meter squared per year for 4 different sediment traps that are off the coast of West Africa. So you can see the numbers are around 4, 11, and 18. They increase to the south, and that's because the dust trajectory is actually in this direction. And so this sort of southward loading of the dust is what you expect, and that's what you see in the sediment traps, these actual ocean-based measurements over a given year. And then these are the particle fluxes estimated using the thorium normalization. And you see not only do the numbers agree pretty well, but you also see that same latitudinal trend. This is work by David McGee. So jumping right into the data, we published this paper last year in EPSL. This is going from a core that's furthest to the south. This is actually that GC68, the core that Jess was talking about toward the end of her talk. And this is to the north. This is actually near Cape Gear, which is actually where Edouard had his core. And in all cases, we've got increasing dust fluxes pointing up, and this is going from 0 to 20,000 years. And so where you see the AHP, this is the African humid period, the period of low dust fluxes. There's low dust fluxes in part because it was wetter at this time, and so the production of dust was less. And you can see it increases up toward the late Holocene in all the cores. But the main thing is that during the younger Dryas and during the Heinrich 1 layers, you can see that these are really much, much higher absolute fluxes of dust that are being deposited in the oceans. I think the most effective way of looking at this is not so much this recognition that this whole margin of West Africa witnessed the African humid period, but if you scale everything to the dust flux values of the African humid period, so it's scaled to 1, and then just allow the values to change in proportion in each core relative to the African humid period, you can see that modern dust fluxes are about 2 to 5 times higher today than they were 5 or 10,000 years ago during the African humid period. So it's a really dusty place there today, and 10,000 years ago it was a place that was between 2 and 5 times less than what it is today. So there were pretty clear sky conditions off the margin of West Africa during the African humid period. But what's really remarkable is just how dusty the younger Dryas and the Heinrich events were. I mean, this is 13 times greater than the African humid period. So it was a much, much drier and windier and dustier time period during these stadial events of the younger Dryas and the Heinrich events. And the glacial dust fluxes are between 4 and even greater than 10 times higher than the African humid period. I put this up here not so that you can see each one of these wiggles, but that you can see that there's sort of a broad hump in each one of these cores. This is the African humid period, this sort of broad gray interval here between 5 and 10,000 years ago, and it's measured all the way up where this red line is. What's interesting, and I'm going to return to this later, is that this one core here in Cape Gear, where Edouard was discussing his results, there's no evidence for this interval of what would be high calcium carbonate or low dust fluxes across this transition. And so I'm going to return to it because Jess has actually measured the plant wax delta D in here, and actually we do see this humid period in the plant wax information, but there's no dust signal that goes along with that. Returning to this issue that Jess brought up, if we look at the influence of sedimentary mixing, and I bring this up only because some of you who are paying attention will notice that, well, this is my ODP site 658 here, and there's that abrupt transition. But then you could easily ask, well, hey, that one looks pretty gradual, and that one looks pretty gradual, so does that one, so does that one, so does that one. Actually, most of these look pretty gradual. And you can say, hey, Stefan's right, that it's actually really gradual along these cores. But then you have to ask the question, well, why is it gradual? And it turns out that if you measure the duration of the transition in years, that's apparent in your sampling, and then just plot it versus the sedimentation rate of each individual core, you'll see there's a pretty decent correlation between the two, such that as you move toward an infinitely high or a higher sedimentation rate, this begins to asymptote on some kind of a value of the transition duration, which is less than 1,000 years. So in other words, the higher sed rate core that you have, the more faithful is the representation of the actual transition time of the African humid period as measured by this proxy. And that number ends up being something on the order of a few hundred years. David McGee, in this EPSL paper in 2013, actually did this in a quantitative way. So if I can just show. So if this is time here, and then this is, let's just say, dust in here, if you have a square wave transition, so if it's just a very rapid transition that occurs, let's say within a single year, if that happened in every core, and the cores were not having any bioturbation, then it would appear as a square wave. But the problem is that deep sea sediments have organisms on the bottom of the floor that are mixing up the sediments. They're basically mixing sediments to a depth of about 10 centimeters. So what ends up happening is you get a signal that looks like this, and then you have this transition that goes like that. And so you end up getting a smoothing depending on the sedimentation rate. The slower the sedimentation rate, the more the smoothing. And so we actually looked at this explicitly in this case here. We looked at that explicitly looking at the transition out of the African humid period and into the African humid period. And the transition, actually it should be the other way around, I'm sorry. You'll see these data points in black are the actual measured observations. And applying this single mixing model to the observations gives rise to what the transitions would have looked like if you could unmix them. And the dashed line is what it would look like if you could unmix it. In other words, the data that we've measured are consistent with an instantaneous transition that occurs sometime around 5,000 years ago for all of these cores. So the take-home point here is that at least for these cores that span about 12 degrees of latitude, was around 4.9 thousand years ago, plus or minus a couple of hundred years. So I had mentioned that there are these dual influences of high and low latitude climate forcing on the African monsoon. So as Jess pointed out in her talk, if the African monsoon were just linearly responding to orbital forcing, this is the orbital forcing going from 0 to 20,000 years ago, it would look just like this. The records that we have for the monsoon, this is just one, but we could use ours as well. This is the Gulf of Guinea sea surface salinity reconstruction from the Niger River outflow. These are actual observations. You'll see that it's kind of clipped. The first half of the African humid period is missing. And the reason why it's missing is because it's punctuated by the Younger Dryas and then the Heinrich event afterwards, the glacial. And so the very rapid transitions that we see with the Younger Dryas or after the Heinrich events, those rapid monsoonal transitions, and in particular the very end of the Younger Dryas transition, these very rapid transitions have been linked to these cooling events in the North Atlantic, such that when you have cold sea surface temperatures in the North Atlantic, a large number of climate models have shown that actually sends the ITCZ further southward, and it leads to drier conditions, and hence these higher dust fluxes at this time. So the African humid period, if the Younger Dryas didn't exist, or if the glacial weren't here, would probably look a lot like this, and that's what we see actually for, let's say, stage 5E during the Eemian. So Rick Chilingi in 2009 published what I thought was just a beautiful paper. They actually worked on a sediment core exactly on top of our core off of Mauritania. And in this core, they measured the grain size distribution. So this is a log normal plot of age going back to 120,000 years ago versus the grain size that's measured in the core at very high resolution. And basically where you see these bright colors indicate where the modal grain size exists. So this one here, for example, over the last 10,000 years is something less than 10 microns. But then when you get back around 14,000 years ago, it's pegged on this much coarser grain size at around 60 microns or coarser than that even. And you'll see there are some regular oscillations that go back and forth. And so Jan Berend Stoot has been a leader in this, what's called N-member unmixing of grain size distributions. And what he discovered is that, particularly for these cores off of West Africa, there exists 2 or 3 N-members. One is fluvial mud, which is very fine-grained, which is what's happening here during these wetter intervals. And then during these drier intervals, during the glacial, for example, you have 2 different kinds of dust, a fine dust and a coarse dust, but it's distinctively much coarser than what you're seeing in the fluvial muds. And so they developed a proxy for doing this in this core. And so if this is just the predicted orbital forcing, and these red bars here would be the past African humid periods, this is their grain size record in green. And you can see there's the African humid period there. There's another one here at stage 5A. This is another one at stage 5C. And then if you had 5E, it would be another one over here. The core didn't go that far back. But then you'll see that it's punctuated by these other time periods which were distinctly drier. In other words, coarser grain sizes. And if you actually look at the North Atlantic sea surface temperature record over this time period, you can see this progression of Heinrich events and Dansgaard-Oeschger events, these stadial events, that correspond just beautifully with these cooling events. And so this is this dual influence on African climate, the low latitude monsoonal forcing from the orbits, and then the high latitude imposition of dry and dusty events during stadial times. Another way to look at this problem is a paper that's in review with Louisa Brattmiller. And again, it's looking at these same cores that we have off of West Africa. And instead of looking at dust and the winds and trying to infer changes in winds from the dust record, what she did here was to look at the proxies for upwelling here. So this is the northeast trades as they parallel the coast. Being in the northern hemisphere, that causes the waters to be moved away, that is at right angles, away from the coastline. And so that results in upwelling of cold, nutrient-rich waters to the surface. And that feeds this very high productivity. And that's what's colored in this ocean sea whiffs image. Wherever you see these warmer colors are where there's more chlorophyll in the oceans. And you can see there's lots of upwelling here at this location. So the idea that she was looking at was, are there changes in the gradients of upwelling along here that are linked to these climate cycles that we're looking at? And indeed there are. This is just one core that she published. This is the same record that Jess was talking about, GC68. It's the one it's this site furthest to the south. And in black is actually shown the opal flux. This is, again, this thorium normalized opal fluxes. And you can see there's the Heinrich event, there's the Younger Dryas, and then boom, very low productivity during the African humid period, an abrupt transition out of the African humid period, and then a steady increase to modern values. Same thing for the organic carbon flux, shows the same timing and pretty much the same wiggles. And then comparing that to the dust flux, it's almost exactly the same signature and the same timing of the transitions. So the take-home point we would have for this is that the aridity changes and the wind speed changes were linked, and that's what was pacing the upwelling along the margin. And so this is that same core that I just showed earlier. This is another core further to the north, another one further to the north of that, and another one further to the north of that, albeit at very low resolution. But you can see the same story. During the glacial, the upwelling is increased, particularly during the Younger Dryas and the Heinrich event. During the African humid period, the upwelling kind of shuts down, or it's at relatively low values. But what she did was a pretty clever thing. What she's going to do next is to compare the gradient in the absolute flux values between this southern core and all these other cores. And something emerges, which is that during the Younger Dryas and the Heinrich events, during these cold events, this locus of high productivity shifts further south. Basically, you get the largest transitions occurring in this core, and it's basically reducing the productivity that you see in these other cores. So it's really being driven. What you're seeing is a southward shift of the winds and the productivity during these cold events. So the next question is, where did this dust come from? And is it really representative of a big area, or is this just something that's linked to what's happening along the coast? And we do this by actually a completely different set of geochemical measurements that look at the sediment geochemistry using radiogenic isotopes and major elements to examine the chemistry of the dust itself and say something about where it came from, because we have similar measurements from the African continent. And the African continent has a really broad terrain, but most of what you see here is this kind of buff color, which are Mesozoic and Cenozoic sediments. But particularly along the coast, there are these sources of Archean rocks, which have a much more negative epsilon neodymium value linked to these rock compositions. And so if we were seeing a change in the source area of these dust pulses, and then that might argue that, well, actually, the dust records that we're seeing are actually just reflecting different contributions from different parcels of land, or different parcels of the North African continent. Instead, what we see is that if this is the Archean terrains, those red splotches on the map, this is epsilon neodymium versus strontium isotopic cross plot. Our data all plot up in this area, which is consistent with source areas in these tan areas, and in particular the Beaudelet Depression, which is the area that Florence was talking about, which is today the source of dust. So the take-home point from this analysis is that the source of the dust in the past is the same as what it is today, which is these regions here in the interior. It's not a very surprising result, but it's an important one. One way we can confirm that is that the epsilon neodymium values are just constant throughout this whole interval. In other words, it's not changing at all. But one of the things we did find out that was really surprising is that when you look at the strontium isotopic composition of the dust, it has a signal that looks very similar to the terrigenous percent record. And this kind of really, we were scratching our heads about this, because the neodymium data is saying absolutely the host rock where the dust is coming from has not changed over this time period. But the strontium isotopic composition has. And so we looked into why that was. It's suggesting a change in the sediment processing during the African humid period. In other words, how the sediments are being weathered and transported. But that was just a starting idea. We really had to prove that. And so this is where the major element geochemistry comes in. Some of you may know these what are called ternary diagrams, where you perform major element geochemistry on the prepared samples and plot it in a ternary space of aluminum versus potassium versus calcium and sodium. So obviously the rocks that are, let's say kaolinite would, for example, be up in here, and biotite is over here. This is the average shale composition, so if you take an average shale, it would plot where that red circle is. What we find is that the core top values are here in the yellow, and then during the early Holocene, you see this transition toward this edge, which is basically moving toward kaolinite, in other words, toward a more weathered sediment. And all this is telling us is that during the wet phase, the dust that's produced at that time was itself more weathered, more leached. Again, it's a consistent result with it being more humid. And so you can actually come up with a proxy for this weathering, and you can see it actually plots along the dust flux value really well. And I'll just leave it with one additional comment, which again, I think one of the things I was hoping we could do with this meeting is to try to find ways to reconcile our different views. And I think this is one way that does help. Using this geochemical method, you can separate the fluvial contribution from the aeolian or wind-blown component. And so the total integral of this plot here is actually the thorium-normalized particle flux over time. So it's high during the Younger Dryas, it's high during the Heinrich event, it's low during the African humid period because it's wet, there's not much dust, and then it increases again in the latest Holocene. What's interesting is that during the African humid period, most of what's being delivered there has this weathered signature, which could be interpreted to be fluvial in nature. And then that wanes away and gets replaced by this increase in the dust after. So yes, there's kind of a rapid transition in here, but it's not one that's occurring on decades. It's occurring over a millennium or so, but it is a broader transition. So I know we've done a lot here, but the summary so far is that the African humid period is apparent along the entire West African margin. In the signals that we see, there's obviously very clear evidence for this low latitude orbital monsoon forcing by precession. By far the lowest dust fluxes occurred during the African humid period, and it ended in these cores at about 5,000 years ago. And the transition times were on the order of centuries, but not many millennia. The dust fluxes were between 4 and 10 times higher during the stadials, during the cold events. And during these times, based on the upwelling evidence, we know that the trade winds were a lot stronger then. So the winds were much more competent. So this raises the question, are we just seeing winds here? Is this just the competence of the winds carrying available dust out to the ocean or not? In other words, is there some kind of a decoupling between our interpretation of aridity versus changes in the wind speeds? And so here we feature Jess when she was at Lamont, and she's not in front of a mass spectrometer there, but you can forgive me for that. This is just a restating of what she presented in her talk, is that we can use plant wax biomolecules, a stable carbon and hydrogen isotopic analyses of them to infer past changes in paleohydrology. So what's so powerful about her work is that it really allows us to address the thing we most want to know about, which is changes in the rainfall availability at the site. This is another way of illustrating what she mentioned in her talk, but this is the month of August. This is actually a spatial map, interpolated spatial map from observations of the hydrogen isotopic composition of precipitation during the month of August, which is the monsoon season. And you can see this big patch of blue here. These are very low hydrogen isotopic values. And these very sort of low hydrogen isotopic values correspond with wetter time periods. And so this is what we would expect to see in the cores when it gets wet, not when the winds are changing, but when it's actually physically less wet. When you have changes in rainfall, you expect to see this in the hydrogen isotopic composition of the plants, because you are what you eat, and so the plant is actually recording its isotopic composition of the water it's drinking, and that's preserved in these fats, as she mentioned. And this is a summary of data from 5 cores, again from the same transect of cores. This is that core 68 that she showed today in a much higher resolution version of this figure. And then you'll see this green signal here is that green one here, the yellow is that one, and this orange is that one, and the red is GC27 near Cape Gear, where Edouard's core is near. And in all cases, including this core up here, there's very clear evidence for isotopically depleted values, lower delta D numbers of the plant waxes during the African humid period. And as Jess made abundantly clear in her talk, that these transitions are far, far more rapid than you'd expect from just a linear response to orbital forcing. So, the take-home point for me when she produced these data is that there's unquestioned evidence that the African humid period extends along this whole region, and that the transition occurred roughly around 5,000 years for all the cores that we studied. What's interesting, and a point worth making, is that if you look at the southernmost site here, this blue core, you'll notice that during the younger Dryas, this shift to drier conditions and the Heinrich events, you'll notice that the Bowling Alarid here, which is a wetter time in the southern core, the African humid period for that southern core would probably extend to include this time before, of the Bowling Alarid, and then interrupted by a dry spell in the younger Dryas, and then the African humid period proper. But as you go further north, let's say to the northernmost site, which is this one up here, this is the extent of the African humid period. It's really just after the Younger Dryas to about 5,000 years ago. So the southern sites have a longer humid period, if you will, and the more northern sites, it appears to be restricted to the African humid period as we would interpret it more generally. This is just to echo the point that from Jess's core, from this site here in the Gulf of Aden, on the other side of subtropical North Africa. This is actually, these are not core sites, these are actually pirate attack locations. Our crews actually left from Dar es Salaam, we went through here, it was just crazy. We were there about 2 months before 9/11, and we operated under radio silence, all the ship's lights were turned off. It was pretty stealthy. We were aboard the ship, the Pelagia, which is a Dutch flag ship, and I'm convinced if it was an American flag ship, I wouldn't be here today. But the cruise was worth it, if only to produce Jess's record that we have here. It's just a phenomenal indication of just how rapid these transitions were, and also how large the rainfall changes were, and also how consistent they are with the lake records along the East African Rift Valley as well. So this is a good lead-in, I think, for Yannick Garcin's work, where he has similar evidence for a very rapid drawdown of the lake level in Lake Turkana by about 50 meters that occurred at exactly the same time, about 5,000 years ago, as what we see in Lake Turkana, or this record from West Africa, and now Jess's record could be compared here too. Very rapid transition in the actual level of the lake itself, and I don't think you can have a stronger indication of paleohydrology than that. So with that, I'll just leave it, and I'm ready to take questions. Thank you.